Welcome to Ask and Learn.
Okay, we're going to start with the steam reforming equation. So here, oops, sorry, didn't mean to do that. All right. So here we have our chemical equation, and we're looking for delta H and delta G. So the best way to get delta H is going to be to use our delta H of formation values. The best way to find delta G is going to be to use this equation. So we're also going to have to find our delta S. And then we'll be able to plug in our delta H and delta S and temperature to get our delta G. So we know that the temperature is 1,000 degrees Celsius, which would equal 1,273 degrees Kelvin. All right, so let's start with finding our delta H of reaction. So again, we're going to do products minus reactants using our delta H of formations. And remember, you always want to add in any coefficients that are in the chemical equation. So I have provided the delta H of formations, but you could also find these in your textbook or you could Google them. I didn't put the units, but it's always best practice to put the units. So remember to always fill in the coefficients. And if you want to pause the video and get that calculation done, you should get a 206.2 kilojoules. So we know that we're going to put this in equation with entropy, which is in joules. So let's just change this into joules by multiplying by 1,000. We'd get 206,200 joules. Great. So we're going to do the exact same thing with our standard, our delta S reaction. Again, we're going to do products minus reactants. You should hammer that into your brain for these types of problems. And I have the little skeleton again. Remember, add your coefficients. And then again, I've provided the values, but again, you could look them up or they should be in your textbook. So we're going to add times 3 there. And then if you want to go ahead and pause the video and do this calculation, you should get a 214.5 joules. All right, so now since we have our delta S and delta H, we can plug them into our initial equation right here, put a 1 by it. So we'll plug in, making sure we use the same units. So 206,200, oops, missing a 2 there. Sorry, that's a little messy. And then we know the temperature is 1,273 Kelvin. And then we have 214.5 joules. And that should give you a delta G value of negative 66.89. kilojoules. So you will get the value in doing this calculation will give you the value in joules. So I just divided by 1,000 to get kilojoules, just in case you're getting confused on that step. All right, so we're going to do the exact same thing for our water gas shift. Again, we're doing products minus reactants. I'm sure you're getting tired of me saying that. So I have our skeleton written out here. Thankfully, we don't have any coefficients, so we don't need to worry about that. I have not given you the delta H of formation values, so if you want to go ahead and look those up and plug those into the equation, I'll give you a minute. If you want to pause the video, you should get negative 41.2 kilojoules. And then you're going to repeat that for your delta S of reaction. Again, go ahead and look up the standard entropies. They should be in your textbook. All right, so once you do that, you should get negative 41.9 joules. And then again, we're going to plug this in. So we want to change this to joules. So we're going to be multiplying by 1,000 to get joules. So 41.2 times 1,000 gives us 41,200. It's pretty messy, but there we go. We'll just plug these into our first equation again, 41,200. Oh, and remember the negative. And then negative 41.9. Oh, that's actually for our temperature. I'm jumping the gun. All right, this is our 1,273 Kelvin, and then we have our negative 41.9 for entropy. Great, so when that is done, you should get 12.1 kilojoules. Again, you're going to get an answer in joules, but just divide that by 1,000 and you will get 12.1 kilojoules. All right, moving on to letter B. So it asks us for the delta H or the delta G of reaction of these two reactions we just worked with. So this one here and this one here. So we just have to add these together since we know the delta H of reactions for both. So we know that this one is 12.1 kilojoules. And this one is, let's see, where did I put it? Negative 66.8 kilojoules. There we go. All right, so we know we want to get a final equation that looks like this. 2CH4 plus 3H2 going to CO2 plus CO plus H2. Okay. Oh, not H2O, just H2. Great. So in order to do that, we're going to multiply this whole reaction times 2. So that will give us 2CH4, 2O2, 2CO2, and 6H2. Oh, and excuse me, we want a 7 here. All right, so by doing that, we also want to multiply this by 2, our delta H of reaction. And you know what? These should be delta G's. So sorry about that. It's one of those days. These are our delta G's of reaction. All right, so now we can just go ahead and add these equations together, which will give us this equation down here. So again, we have our 2CH4s. We have 3 H2Os. We'll cancel one CO on this side, so we'll have our 1 CO, oops, wrong way, our 1 CO and our 1 CO2, and then we will have our 7 H2s. So that means we'll also just add these two together. So first we want to multiply 2 times negative 66.8, and then you're going to want to add 12.1 to that, and you should get a delta G value of negative 121.7, negative 121.7. And you're going to want to remember this because we will be using it in the next two problems. Okay, so the next two get a little bit tricky. So we're told that we have this reaction at 98 ATM and it's 50% conversion. So we're trying to find delta G. We can use this equation here. Delta G equals delta G standard of the reaction plus R, which is a constant. It's 8.314. Temperature, we're told it's at 1,000 degrees Celsius, which again would be 1,273 degrees Kelvin. And then the natural log of the reaction quotient here, that's Q. So using the 98 ATM and the fact that it's a 50% conversion, we can find Q, and we can do this in partial pressures. So I'm just going to say PP for partial pressures. So the first thing we want to do, though, is the 50% conversion. So the best way, or the way I like to do this, is to use an ICE table. So let's say we start out with our initial, I'm just going to do the moles we have here. So 2 moles of CH4 and 3 moles of H2O. And I'm doing that again because the coefficient here for the balanced chemical equation. And initially, if it was 0% conversion, we would have 0 CO2, 0 CO, and 0 H2O. The change, so I is initial, C is change, and E is equilibrium. So the change is 50%. And you want to make sure you always add the stoichiometric ratio to this change. So we know it's 50%, so we're going to say 2, which is the stoichiometric ratio, times 0.5, which is 50%, and this will be subtracted. So that's the change, that's the conversion. So 50% of these reactants are going away, and we'll do the exact same thing for H2O. And then adding to this side, we'll do the exact same thing, but instead we're adding 50%. So add 0.50 plus 0.5, and then plus, again, always use your stoichiometric ratios, plus 7 times 0.5. All right, times 0.5. All right, and now we're just going to find our equilibrium. So that's just taking our initial and either subtracting or adding. So 2 minus 2 times 0.5 is just 1. 3 minus 3 times 0.5 is 1.5. And then we have 0.5, 0.5, and 4.5. All right, so now we know our molar concentrations. So the best way to do the partial pressures is just a ratio. So we know, let's just do CH2 to start with. So we know we have 1 CH2, and then we know that this in total is, we have 1 mole plus 1.5 is 2.5, plus 0.5 is 3, 7. This should be a 7. We have 7 in total. Great. So, and then we know we want to find the partial pressure of this, and this is our 98. And that should come out to give you 14. So that is going to be the partial pressure of CH4. So you go ahead and try those for the rest for H2O, CO, and CO. So you'll just be substituting this number here with the numbers we found at equilibrium. Great. So then we're going to find our reaction quotient using our partial pressures. So our reaction quotient is products over reactants raised to their coefficients. So for CH4, which will be on the bottom here, its coefficient is 2. We know it has a partial pressure of 14. For H2O, it has a partial pressure of, 1 minute here, of 21. Sorry about that. 21, and then we have 7 for CO2, 7 for CO, and 49 for H2. Great. So now you're just going to solve for Q, and that should give you 1.8 times 10 to the 7. All right, now we can plug this back into this equation here because we know everything. Again, we solved for this delta G of reaction in the last step. So plugging everything in, sorry, we don't have too much space left. Delta G equals delta G standard, which was negative 121.7 plus, oh, and you know what? I almost skipped a step. So we know our 8.314 is in joules, so we want to make sure that this is also in joules. So again, you're just going to multiply by 1,000, and you should get 121,700. Oops, sorry, that's a little wonky. All right, so this is going to be 121,700 700. Sorry, that's a little messy. Let me try with red here. 1, 2, 1, 700. Okay, that's a little bit better. Great, and then we have our R and T, 8.314 plus 8.314 times 1,273 Kelvin and times the natural log of 1.8 times 10 to the 7th. So go ahead, pause, and you should come out with a delta G of 55.1. Again, that is in kilojoules. So I just divided the product of this by 1,000 because this should be in joules. So since this is positive, we know that this at this point at 98 atm pressure and 50% conversion, the reaction is non-spontaneous since we have a positive delta G. All right, so we're going to do the exact same thing for our 90% conversion. I haven't written out our ice table, but you're going to do the exact same thing. So instead of 0.5 here, you're going to want to put 0.9. And then you're going to do the same exact thing using a ratio to solve for the partial pressures. So let's put, I'll do red for this second problem. So 0.9, 0.9, 0.9, 0.9, and 0.9. Great, so that is going to give you different equilibrium concentrations for each one. You're going to add those all up as the total, and that total is going to go here, let's say Y, and then you're going to do, so for CH4, you put in whatever you found for the equilibrium and equals X over 98, and you will find the partial pressure. So go ahead, pause the video and try that out. If you're confused, rewind the video and watch this ice table again, and that should help you out. All right, once you have done that, you should find the partial pressures to be 2.3 for CH4, 3.4 for H2O. And again, we're using the same exact quotient or reaction quotient equation for the next one too, since it's the same chemical equation. And then you're going to have 10.3 here, 10.3, and 71.8 here. Great. If you solve that out, you should get a Q equaling 5 times 10 to the 22nd. And again, we're going to plug this back into our first equation. So our delta G is going to equal negative 121700. That is our delta G for the reaction, delta G reaction. And then that is going to be plus our R constant, 8.314 times our temperature, times our temperature, 1,273 Kelvin, and then times the natural log of our reaction quotient, which again is 5 times 10 to the 22nd. And you should get a delta G of 188 kilojoules. Again, you're going to divide the product of this by 1,000 since we want to get it into kilojoules. Okay, kilojoules. Great. So again, since this has a positive value, a positive delta G, it is non-spontaneous under these conditions.